Hi, I'm Sam Ben Yaakov. The title of this presentation is the Flyback converter. This converter belongs to the family of converters with isolation, and as such it is extremely useful when designing a DC to DC converter to operate off the power line. The Flyback converter is extremely popular, used in many applications, including chargers and other applications. Let me just mention that the name Flyback comes from a analog TV circuitry in which there was a beam of electrons sweeping the screen, and the Flyback circuitry was actually responsible for moving this beam and then bringing it back very quickly, hence the name Flyback. Before starting with the topology itself, with the circuit itself, let me say a few words about coupled inductor, which is the basis of this converter, of the Flyback converter. Now, a coupled inductor is something that looks like a transformer, but it is not a transformer. The difference being that in a transformer, if you have current coming in, say in one winding, it'll come out from the other winding, and no energy is stored in the core. Now, in the case of a coupled inductor, being an inductor, when you have a current coming in, there may not be any current coming out at this point. Energy is stored in the core, and then at a later stage you can get this energy back through another winding. Nonetheless, when you look at the ratios of currents and voltages, the coupled inductor behaves in this respect like a transformer. It's also important to note that the ratio of the inductances seen from each winding here and here is the ratio of the number of turns squared. So once you know the inductance in one side, you can calculate the inductance on the other side if you know the turns ratio. Let me go and mention another point which is sometimes misunderstood. We all have the feeling that if you have a current through an inductor and then you interrupt it, you'll generate high voltages. The reason being that the state space equation of an inductor states that voltage is L times the IDT. Interruption of the current in an abrupt way means that the IDT is very high, consequently a high voltage will be generated. Now, in a coupled inductor, the situation could be that when, say, this is now a coupled inductor with two windings, 1-to-1 in this case, and say this switch is on and current is flowing in this direction. This here shows how the switches are controlled, this diagram. Here is switch 1 and then switch 2. Now current is going in, building up into a magnetic field, and then at this point of time, S1 is opened and immediately S2 is closed, shown here. Well, the current went into the dot in here, it'll still go into the dot in here, it'll continue here, and there is actually no interruption of the magnetic field. So you can interrupt the current if the magnetic field is sort of supported by another winding, another current. Now, in the case of a coupled inductor, which will be connected, say, to two voltages, and here's again the same switching arrangement, what you will see is that when V1 is connected, current will go up linearly because the IDT, we just said it actually in just what different way, is V over L. V is constant, L is constant, so you'll have a constant slope here. There is an interruption here in terms of the switches changing, like S1 is open and then S2 is conducting. And consequently, the current, if this is a one-to-one, the peak current will be exactly the same, and the current will now go down. The reason it will go down because I've put here a voltage of reverse polarity. So when the polarity is reversed, there's the IDT of a different polarity too. Okay? Important to know that in this case, the I peak and I peak will be the same. Now, in the general case, if it's a 1-to-n ratio, then of course what you'll see is a similar picture in terms of voltage, the current going up because of the constant V1 voltage when S1 is on, and then there is a switching of the current to the other winding. You'll see another magnitude of I peak 2, and then a slope which will be different. Why different? Because if you have a ratio of 1-to-n, then the inductance you see here is, let me write it down, n squared L. If this is L of the primary, there is n turns here, so this is the inductance of the secondary. Also, since we have 1-to-n ratio, the peak current, I peak 1 times 1, should be equal to I peak 2 number times n, and consequently the peak current will not be the same. They'll be just the same ratio of the turns ratio. The slope then would be V2, here's V2, divided by the inductance seen through this winding. So these are the very, very basic relationship that we would need in order to understand the operation of the flyback converter. Let me just go one step ahead and say that actually we do not need two switches. We can, instead of say S1 and S2, S1 opens, we can just put one switch and a diode. What will happen is that when the switch is turned on, S1, the voltage imposed in here will cause the voltage of this polarity in here, and consequently the diode will be blocked because the polarity is reversed, and at this point or at this stage energy will be pumped into the magnetic core. Now once S1 is turned off, there's no current here. Now the current will start building up. Now what direction will be the current? Well, we can look at two ways. One way to say that if the current was going into the dot here, then it'll go into the dot here, meaning that this will be the direction of the current. So it'll be going through the diode, and in this particular case developing a voltage which is plus here and minus here. Okay, so we really don't need two switches. We can operate the circuit with one switch and one diode. Let's now go one step perhaps backward and talk about a buck boost converter, which is the actually the basic topology on which the flyback is developed. Now the buck boost converter consists of an inductor which is connected by a switch to a power source, and then the switch is open and the current will go this direction, developing a negative voltage here. And it's easy to show that you have a turns ratio of V out to V in. This is the gain of the stage. It's D on over D off. D on, D off are defined by the on time of the switch. This will be T on. This will be the period and T off is the complementary. So the ratio between T on and T is defined as D on. And similarly, T off over T is D off. Okay. Now, what we can do, instead of having one inductor, I can use a magnetic element which has two windings on it. That is a coupled inductor. And as before, we'll have a primary in which we actually pump in energy, and then a secondary in which the energy is released out, so that when the current goes in here, and then it'll go this way, and we'll be circulating, and we'll get a voltage like this. This is, in fact, a flyback converter. Okay? We have a coupled inductor. We charge the magnetic element with energy, and then release it into the load with a second winding. So the operation of the flyback converter is very similar to what we have just discussed. This is now drawn in a more conventional way. This is the power source. Well, I'll show it as a battery, but this could be like a coming off the power line with just a bridge rectifier and having a voltage of this polarity. Switch is turned on and off at a given duty cycle, okay, of D on, and as before, we have the two stages. One, during T on, energy is stored. At this time, the polarity is like this, and therefore this diode is reversed biased, so therefore it's non-conducting. And then during T off, this is off, current is flowing now this way. Why this way? Because I've sort of turned the winding so as to ground, sort of have a reference line here at the dot and the output at the other line of the winding, so that I'll get, in this case, a positive voltage, like currents going in here, it'll go in here, and therefore it's positive voltage. So in fact, since the secondary is floating in terms of ground with respect to the primary, you can call ground any point you want in the circuit, so you can get a positive voltage or a negative voltage, which is of course very, very convenient. Now, one thing to realize is that during the off time, the T off, there is a voltage which is building up across the switch. The switch, of course, will be like a MOSFET transistor that is controlled by a gate signal, and the magnitude of this voltage will be, first of all, V in plus the voltage developed in here. Why there is a voltage here? Because the coupled inductor acts also as a transformer, in the sense that if there is a voltage in here, and this voltage is in fact V out, I mean, save the voltage drop on the diode, then through the turns ratio, it'll be reflected to the primary, and could be, by the way, larger or smaller than 1, depending whether you like to have a low voltage at the output or a high voltage. Now, flyback transformers are used to, say, generate 5 volts, so therefore, if you start with 100 or 200 volt at the input, it'll be a step down. Now, in some cases, we would like to generate extremely high voltages, then N could be a very large number. Okay. Now, what will be the voltage gain of this stage? That is the ratio between V out and V in. Okay? Well, there are a number of ways to do it, and one is using the average voltage method, which states that the average voltage on an inductor And in this case, it will be on any one of the windings of this coupled inductor. The average must be 0, because if not, then the average rate of change of the current will be non-zero. This line stands for average, and this is average. So if this voltage, the average voltage on the inductance is not 0, the IDT, the average, will not be 0, so the current will start climbing up or going down, and so this system will not be in a steady state. So if you assume that this, and if it is in steady state, this relationship must hold. Okay? So you can do this calculation looking at any one of the winding, and I choose to do it here. And what I see here is that during the T-on period on this winding, there is the voltage of V in, while during the off period, you see the winding, the voltage of the secondary reflected through N. So it'll be V out over N. Now, so therefore, this area must be equal to this area if you want the average to be 0. And this is exactly what is done here, and we get this relationship. Now, of course, the plus minus here is really the question, which side do you actually call ground? Or if it's completely, of course, floating. Now, the difference between this relationship and the one for the buck-Wurst is this N number. So by having a turns ratio, you can in fact get extra gain, which is of course very useful in many applications. Another very important feature of the Flyback converter is the fact that you can have multiple windings. That is, you can have more than one output. How does it work? Well, during the on time, the story is the same. You are storing energy in the coupled inductor. This is now a coupled inductor in this case with 3 windings. And then in the discharge state, that is in T off, energy will come out from here and energy will come out from here. And it will feed the output section here and here. Now, since again the voltage ratios are the same here as in a regular transformer, the voltages, the relationship of the voltages of V out 1 and V out 2 are like the ratio of the number of windings. It should be V out 2 over V out 1 is N2 over N1, and not as printed here by mistake. Okay, let me just sum up what are the characteristics of a Flyback converter and why is it so useful. First of all, we have isolation, excellent for the offline application. We have this capability of step up or step down. We can have a higher voltage, low voltage, as needed in a particular application. A disadvantage is that if you look at the current at the primary and at the secondary, you see the current sort of interrupted. I mean, it's not continuous. This is now the current coming out, because during the on time there is current here, during the off time there is current here. And this pulsation causes ripple and noise, so this is not a very desirable feature, but this part of the characteristic of the Flyback converter. A very important and useful feature is the fact that you can have multiple outputs. Makes it very economical. You can have a number of outputs, and also the economics is actually even higher, considering the fact that you do not need an inductor per each output. In other topologies, like in a forward converter, if you like to have a number of outputs, you'll have to put a filter, you might say, inductor on each one of the windings. Of course, it's bulky and costly. So the Flyback really has some nice feature, and this explains, of course, why it is so popular. This brings me to the end of this presentation. I thank you very much for your attention, and I hope you have found this presentation useful. Thank you.